orbiting electrons around a nucleus is Rutherford's model of the atom. And sorry, I just have to start recording this. Almost forgot. My apologies. I do that every time. We get all excited to start out. Anyway, so let me just backtrack for the recording. Welcome to chemistry, coming alive. Matter is the basis of chemistry, which is anything that has mass and occupies a volume or space. Elements are the smallest form of matter. They're made of substances that cannot be broken down into ordinary chemical means. The atom is the smallest part of the element. And when two or more elements chemically combine, it's known as a compound, such as sodium chloride. Smallest part of a compound is a molecule. And now we're talking about Rutherford's famous gold foil experiment in figure 2.3 of the textbook, where Rutherford shows that the atom is mostly empty space by shooting helium atoms across a gold foil that is hammered down into a very, very thin layer. And with 90% of those helium atoms going through the foil, hitting the screen, it indicated to Rutherford that the atom is mostly empty space. And now, what I want you to do is get up, run right across the room through a closed door, and if you can get through, I'll give you an A for the class. And theoretically, you're able to get through because all of your atoms line up exactly with the empty space of the door, and there's a 1 in 10 trillion chance, roughly, that you can actually walk through the door. So obviously, don't really do that. I don't want you to hurt yourself. That's a little bit silly, but I mean, you're not going to do that anyway. But my point is, it could happen because we are mostly empty space. And that phenomenal bit of information by Rutherford helped us understand what the atom is made of. And let me show you. Basically, this orbiting of atoms, and if you look further in the text, we talk about how much of mass, how much of life is made of these atoms. Look at figure 2.5. The composition of the human body is roughly 96% COH and N, carbon, oxygen, hydrogen, and nitrogen. And again, any atom symbol is found in figure 2.2 of the textbook, the periodic table. You don't have to memorize the textbook's periodic table, but what you do have to know is any of the atoms that are in our lecture notes. So, sorry that I'm repeating this due to the recording, but I just want the recording to have it as well. Okay, so moving along, what does the Rutherford's model show? Rutherford's model shows an electron orbiting around a dense nucleus made of protons and neutrons. What am I talking about? Protons, electrons, and neutrons are known as subatomic particles. And I drew a little chart for you here to help you remember the characteristics of each of these. Protons, electrons, and neutrons. Protons have a positive charge. What does that mean? Well, for our purposes, a positive charge is the opposite of a negative charge. Electrons have a negative charge, protons have a positive charge, and that's what keeps the atom together. Opposites attract, everybody. Positives and negatives attract each other, where electrons circle around a nucleus. The electrons are negative, and the proton is positive in the nucleus, and that centripetal force of attraction keeps the atom together, prevents the electron from just floating out. Neutrons have a neutral charge. Why are they there? Well, they give mass to the atom. Protons and neutrons both have 1 atomic mass unit of mass. Electrons have no mass. Now, obviously, nothing has no mass. It has 1/1836 of an AMU. So we say that the mass is negligible or very little, right? And again, the location, protons and neutrons in the nucleus, and the orbit has the electrons. And why is all this important? Well, we have to understand how an atom looks in order to understand how it's going to behave in the human body, right? How does the atom look? Well, number one, the atom is going to gain and lose electrons to form ions. An ion is a charged particle. And all atoms of the same type have the same number of protons and electrons in a neutral state. So in other words, all sodiums, let's take a look at sodium. If you look at the periodic table in figure 2.2 of the text, it has a number 11 and a number 23. 11 is the atomic number. That is the number of protons in an atom. The larger number is known as the atomic mass. That's the weight of the atom. What do you think the atomic mass will be? The atomic mass will be whatever has weight. Protons plus neutrons equals atomic mass. So let's scroll down just to the definition of this. Atomic mass is equal to the number of protons in an atom. If you have 11, you're sodium. If you have 12, you're magnesium. You're different. And since protons and electrons balance in a neutral atom, right, positive and negative have to cancel each other out, then we know the number of protons and the number of electrons in a neutral atom. So if we look at magnesium down here, our example, it has 24 and 12, right? 24 is the atomic mass, 12 is the atomic number. We look at the little number, and then we just say that's the number of electrons and protons you have. So magnesium has 12 electrons, protons as well, 12 protons. Now, how do we figure out the number of neutrons? You have to subtract the atomic mass from the atomic number. As we stated earlier, the atomic mass is the weight of the atom. It's what has weight in an atom? Number of protons and number of neutrons. So let's go back up to here. The number of neutrons is always given by big number minus little number. That's an easy way to remember it. Okay, and this is on your test. Big number minus little number is number of protons. Little number is number of, sorry about that. Now I've got that wrong. I apologize. Big number minus little number is number of neutrons. I repeat, big number minus little number is number of neutrons. So in the case of sodium, 23 minus 11 is equal to 12. That's the number of neutrons. You have 12 neutrons in a sodium. What's the number of protons? That's just the little number. Little number always gives you a number of protons. So 11 for sodium means 11 protons in sodium. And that equals the number of electrons in a neutral atom. Now, what do I mean by neutral atom? That means it doesn't have a little positive or a little negative on its symbol. The chemical symbol sodium has nothing on it. That means it's neutral. It means protons and electrons are equivalent. All right, we'll come back to that shortly. Why don't we together do hydrogen? Hydrogen has 1 as its atomic mass and 1 as its atomic number. So we take the small number, which of course they're the same, and we make it protons. Equals to 1. And that equals electrons. Protons equals electrons. And then neutrons is big number minus little number. 1 minus 1 is 0. Now I know this number is not big, but it's the top number. Top minus bottom gives you 0. Let's do another one. Magnesium, 24 minus 12. That gives you the number of number of neutrons, right? Big number minus little number. So magnesium has 12 as its number of neutrons. And it has 12 as its number of protons because that's the low number. And the electrons is the same as the protons, so that's 12. Now what is happening here? Now we have charges. A charged atom is known as an ion. Write that down. I-O-N. Write it right over here. I-O-N. I-O-N equals a charged compound. Charged compound means it has a positive or negative charge. Magnesium plus 2 means that you've lost 2 negative electrons. Let's look up here. Electrons are negative, right? Where are electrons? They're on the outer shell. They're in the orbit. Electrons in the orbit. That's the only thing that can be gained or lost. So when we say something becomes ionic, that means it either gained or lost electrons. Now, if you gain electrons, that means you're adding what? Negative charges to the atom. If you lose electrons, that means what? You're losing negative electrons from an atom. Now, I got a lot of sister-in-laws. I got 4. And, you know, many of them don't care for me. So if they come to my party, they're bringing negativity, right? So let's say 3 sister-in-laws come into the room. We're adding -3. Let's say I lose 2 of them. Templay's all happy. Yay. 2 electrons leave. We have a positive 2 charge on my party. Same thing with the atoms. Let's take magnesium here. You've lost two sister-in-laws, right? So 2 electrons, therefore, must have left. Take a look at this normal magnesium, neutral. You usually have 12. If there's a +2, that means you lost 2. So now here, electrons equal 10. Same thing in hydrogen. Hydrogen has a positive charge. So you've lost 1 electron. 1 negative sister-in-law has left. Uh-oh, you only had 1. And that means you have 0. Electron equals 0. Let's together do chloride. Chloride is, you're going to find that very often, that atom, in your health career. Sodium chloride is salt. HCl is an acid, hydrochloric acid. So chloride is often given intravenously to, you know, people as they enter a hospital to keep them hydrated. So 35 is your big number. That's the atomic what? Mass. 17 is your little number. That's the atomic what? Number. So we know from the 17 that the protons have to equal 17. Boom, there you go, 17. You can't change that. That's a nuclear bomb. You have to have that stay the same for every atom of the same type. Now you have a negative here, chloride negative. That means what? Did you gain or lose sister-in-laws? You gained 1. In other words, you gained an electron to make the atom more negative. So usually you'd have 17, but now you have 18 electrons. Big number minus little number equals neutrons. 35 minus 17 is the number of the neutrons, and that is 18. Now, hopefully you enjoyed the little sister-in-law analogy. It's a little silly, and I'm only half joking. Now, to make a long story short, you've got 2 questions on the test, and we can go over it if you want at the end. If you have, if you have a question on how to calculate protons, electrons, and neutrons from an atom, and I would give you the atomic mass and the atomic number. One difference between atoms of the same element is that they can have different numbers of neutrons. That causes them to be isotopes. Atoms of the same element with different atomic masses is known as an isotope. What makes the masses different? It's the number of neutrons that they have. So we are carbon-based compounds. We have carbon-12. That is what we're mostly made of. But there are isotopes of carbon in the environment, which have an extra neutron and then 2 extra neutrons. Carbon-12, carbon-13, and carbon-14. We say that isotopes can be radioactive. Radioactive means that it emits radioactive energy into the environment, okay? Radioactivity can be dangerous, or it does not have to be dangerous. For carbon-14, it's not very dangerous. The waves are not that dangerous. We'll leave it at that. Carbon-12 is what we're made of. That's how you tell the age of an organic compound, you know, how much something deteriorates over time. Now, I don't want to get into the details of it, but isotopes give off radioactivity, and sometimes some isotopes are used in medicine to treat cancer and to kind of attack bad things in the body. We'll leave it at that. And so iodine 131, radium 226 is all used to treat cancers in the body. And that radioactive isotope will destroy certain areas. It's also used to trace and look at images of parts of your body, because the radioactivity that's given off creates a nice image. And I'll leave it at that. So there's 2 uses to isotopes in medicine. But that's what an isotope is. atoms with different numbers of neutrons. In other words, atoms that have different atomic masses. And this carbon is an example. And we're talking about energy, right? Energy of radiation. We've got other types of energy: chemical, electrical, mechanical, and radiant energy. Energy is defined as the ability to do work, to get something done, to clean up your room, put your books all on one shelf, right? All that takes energy. That energy is obtained by chemical energy, energy stored in a bond. ATP, adenosine triphosphate. Circle that, put a star next to it. You got to know it. I think it's on the test. One question. ATP stores energy. I think it's on the test. I recently made up the test, so I think that's on there. ATP stores energy in its high energy phosphate bonds. That's chemical energy. An example: you eat a ho-ho, you eat carbohydrates, you eat bacon, you eat a little fat. We're going to go over all that. That has energy stored in chemicals. Electrical energy is energy of moving charged particles. Sodium and potassium, Na and K, are two ions where sodium flows into your nerves and potassium flows out and creates a moving, what we call nerve impulse or electrical charge. A nerve impulse or an electrical charge is known as a electrical energy. All right, grasp your fingers like that, and that's electrical energy. Then we have mechanical energy. Involves the moving of matter. Okay, I just showed you that. Mechanical. Muscle contractions. My hand is moving. I've changed the chemical energy that's stored into mechanical energy to move. And what's telling me to do that? Hey, my brain. I'm sending electrical signals in order to move my hand. Radiant energy, of course, energy from electromagnetic waves. For our purposes, energy from the sun. And an example of how that's powerful is that ultraviolet light is known to improve your immune system. That's why being outside is good for you in terms of immunity. So with the virus, take a walk, stay away from people, but, take a walk and get some sunlight. It's good. UV light stimulates the skin to make vitamin D. And we believe that that's a part of the seasonality of the coronavirus and why the coronavirus is going down in many areas as we see the season change. All right, it's very complex to predict seasonality, and I don't want to get into that now, but I want to say that it plays a role. Ultraviolet light actually hits your skin and changes the cholesterol in your skin to make it into vitamin D, and vitamin D helps you absorb calcium and strengthen your, strong bones and teeth. You've all memorized that about calcium, but also strengthen your immune system. Chemical and potential, the four types of energy. Oops. The four types of energy, chemical, electrical, mechanical, and radiant energy, really can be divided into two different classes of energy: potential versus kinetic. Potential energy is energy of position, stored energy. We're going to talk a lot about that when we do organic chemistry in about 8 minutes. That's energy stored in bonds in the body. Kinetic energy is energy of motion, movement, and it's actually defined by kinetic energy equals 1/2 mv squared, which is the mass times the velocity squared. And that equation is not right. Just the velocity should be squared, not the mass. Sorry, put the bracket right here. I hate an incorrect equation. So put the little bracket right here. Doesn't matter. I'm not going to have you do anything with the equation. I just want you to know that kinetic energy is energy of movement, how quickly things move and vibrate. Okay, and potential is energy that's stored. Here's a water molecule, here's a bond, that's where it's stored, in bonds. Here's a little joke, after Demplay's first test, a rock goes down the hill. The rock has a high energy of position, right? Then as it goes down the hill, the potential energy is turned into kinetic energy. Potential energy is turned into kinetic energy, all right? and then it has less potential energy. We store our energy in the forms of bonds, potential energy. Each bond is equivalent to a pair of shared electrons, right? Hydrogen has 2 electrons shared, oxygen has 4, and nitrogen has 6 electrons shared. We say that covalent bonds are bonds that share electrons, like a relationship when you share and share alike. That's a covalent bond. Hydrogen, oxygen, and nitrogen bond together in that form. Right? Types of bonding and how matter is combined is really the basis of our chemical reactions. Chemical behavior is determined by the distribution of electrons around an atom. We call that the electron configuration, right? And that is dependent on something known as valence electrons. Electrons occur in orbits, and there's many layers of orbits, just like there's many planets orbits around the sun. There's many layers of orbits of electrons, and electrons in the outermost shell are what are reactive. And electrons strive to get 8 electrons in their outermost shell. All right, let's take the example right here. Here's a sodium. It has 1 electron in its outer shell. Chlorine has 7. What do you think is going to happen? The electron from the sodium is wanting to leave and go to the chloride so that chloride fulfills the 8 electron rule, or the octet rule. So let me restate this. Sodium wants to leave, sodium wants to lose its electron and give it to chloride. Chloride has 7 and wants 1 to make 8. What is sodium getting? Now it has nothing. That's correct, because underneath is 8 electrons, and therefore it has a full shell by getting rid of the 1. The ion that gives away the electron is known as a cation. The one that takes the electron is known as the anion, or the taker. All right, and this is known as an ionic bond. Hint, hint, that could be on the test. A transfer, anytime a bond is formed due to a transfer of electrons, in other words, when one atom takes an electron and another one gives it up, that's called an ionic bond. An ionic bond occurs when electrons are transferred from one atom to another. A covalent bond occurs when atoms are equally shared when electrons are equally shared between atoms. All this is based on something known as electronegativity. Electronegativity is based on how much pull an atom has on an electron. The more pull or electronegativity an atom has, the more it will suck up electrons. Fluoride in your toothpaste, which is what I did my bachelor's level research on for my thesis. Fluoride sucks up electrons really well, and that's why you brush with toothpaste. It pulls the electrons away from the bacteria of your teeth and kills the bacteria. All right. Fluoride is the most electronegative element on figure 2.2 of your text. The more up and to the right you go on the periodic table, the more electronegative it gets. And electronegativity is complex. There's a lot of reasons for it, but the most important reason is the atom nucleus has a lot of pull on the electrons. And that brings us to polar covalent bonds, an unequal sharing of electrons. All right, polar covalent bonds occur when one atom has more electronegativity or attraction for electrons than another. And that is how water forms. This little rho, Greek rho, means slightly charged. Oxygen is slightly charged and slightly more electronegative than hydrogens. So oxygen has electrons around it more of the time than hydrogens, making the hydrogen slightly positively charged. That is responsible for how water molecules work. Let me show you a picture of dissolving. Water dissolves. To dissolve means to basically what? Disappear. Water molecules dissolve in literally, take a look at this picture, a wall of water surrounding the chloride ion. So you put salt in water, or sugar in water, anything charged dissolves in water. And the way in which it dissolves is the hydrogens attract to the negative ions and the oxygens attract to the positive ions, creating a wall of water around the ion and breaking them apart. This is the structure of a water molecule. Bonds between hydrogen atoms and other bonds are very weak bonds, but they are known as hydrogen bonds. Hydrogen bonds are why water is sticky. And if you ever put an ant in a drop of water, which I did as a child because I was a nasty little child, and just watch it struggle, you can see that water is sticky. For all of us, that's important. That's why our lungs would collapse if we didn't have surfactant to keep the hydrogen bonds of the water from collapsing our lungs. Surfactant keeps them held apart. Water and oil cannot mix, and that's a very important principle for the next lecture because oil is not charged and cannot be dissolved. And that's why you have to process in the liver the fat that you eat to be able to have a charge on it to travel through your bloodstream, which is mostly water. All right, so that's the dissolving process. All of these reactions are known as chemical reactions. When bonds are formed, broken, or rearranged, that's known as a chemical reaction, and it is given by an arrow, where to the left of the arrow, there's the reactants, or the stuff acting together, and then to the right of the arrow is the products, what is formed as a result of the reaction. There's three types of reactions: a synthesis, a decomposition, and a replacement. Synthesis builds up, makes new molecules, so A plus B, let's just A and B come together to form C. Decomposition is when A and B are bonded together. See, that's a little bond. When they're bonded together and they break apart, form A and B. And replacement means, well, B is replaced by C. In other words, one thing replaces another. So for example, in a synthesis reaction, a bunch of what we say small amino acids come together to form a protein, right? And I've got some images of these guys. If you look at figure 2.9 of your textbook, it shows the dissolving process of water, okay? And it shows little water striders walking on top of the water. So you get an idea for some of these reactions that are happening. Okay, the next step on our agenda is to take a look at acids and bases. If you look on page 53, figure 2.10, acids and bases are excuse me. Yes, figure 2.10. Sorry about that. Acids and bases are chemicals that either donate or accept hydrogens from solution. So acids and, what do I mean by acid and base? You close your eyes, you think about it. An acid is something that's sour, a base, bitter. You think of it like in your stomach, that's acidy. If you get acid reflux, heartburn, it's from an acid. So you kind of know what acids are, but let's define what acids are. Acids give or donate hydrogens to a solution, and bases suck them up, take them away. So hydrochloric acid in this example gives hydrogens to a solution. Hydrochloric acid, I repeat, gives hydrogens to a solution. And this little dot shows an HCl popping out hydrogens to solution. If something accepts hydrogens, what happens is it pulls hydrogens out of the water that surrounds it, like sodium hydroxide, pulls hydrogens around it, the hydroxide, and makes there be less hydrogen in solution. And it is given and defined by a pH chart. pH means percent hydrogen. pH charts show how acidic or basic something is, and you should know and be familiar with these numbers. 7 is neutral. Having an exact number of 7 is neutral, and that neutral status is pure water. Anything between 7 and 14 is basic. Anything between 0 and 7 is acidic. As you can see, lemon juice is very acidic, 2.0. Milk is slightly acidic, 6.2. Ammonia is very basic, 11.5. You know, the further you are from the 7, the more basic or acidic you are. That's how that generally works. Okay. Our next agenda is to look at buffers. Buffers maintain the pH of a solution. They keep the pH about the same. Your blood has a buffering system to keep its pH between 7.35 and 7.45. That's something you should memorize, what normal homeostatic blood pH is. 7.35 to 7.45. You don't want to go beyond those because it will result in death. And that's a horrible thought, but respiratory acidosis is when the blood pH goes just a bit too much down, right? Now, I want to tell you that you don't have to memorize this carbonic acid bicarbonate system. This is going to be an A2P2 concept. So we're going to skip this right now and move on. But I want you to know that this equation is a buffering equation that keeps the pH of the blood about constant. 7.35 to 7.45. Our next agenda, and if you go on to your chapter, it's to look at carbon. Why carbon? And that's on page 55. We have a picture of the atom, and in your notes, organic chemistry is the study of carbon-containing compounds. Carbon forms large, complex molecules, 100,000 Daltons. Carbon is electroneutral. It always shares electrons. In other words, it forms a neutral atom. As you can see, this thing here is propane, carbon dioxide. This is methane. You know, cows give it off with gas. So do we, by the way. Carbon has 4 electrons in its outer valence shell. And that means, according to the octet rule, how many bonds does it want to form? 4, because it wants to get 4 more electrons. It has 4. It wants 4 more to form 8 electrons. And 8 electrons satisfies the octet rule. We have 4 types of organic compounds in the human body: carbohydrates, lipids, proteins, and nucleic acids. We're going to start with carbs, move on to lipids, move on to proteins, and then finish up with nucleic acids. Then we'll take questions. It's a fairly large chapter. And, you know, if this were during the year, I would have a break right now, and then we'd take questions. But in the interest of time, what I'd like to do is move through the material and then take questions at the end. And we have all the time in the world afterwards. Okay, let's start with carbohydrates. Carbohydrates, if you take a look at your text, figure 2.15 and 2.16, you will see the carbohydrate is made up of generally a little ring. A simple sugar is a ring. And that ring in figure 2.16 is a monosaccharide. Monosaccharide is a simple sugar. And a simple sugar has 3 to 7 carbons in it, in a ring. Glucose forms a 6-carbon ring, ribose a 5-carbon ring. Fructose, which is fruit sugar, forms a 6-carbon ring. And your monosaccharides, simple sugars, build up to form disaccharides. So glucose and fructose come together to form table sugar, known as sucrose. When 2 or more monosaccharides are joined together, we call it a polysaccharide. So a long chain of simple sugars, as you can see in figure 2.16, is a polysaccharide. And the function of carbs is to give you an immediate source of energy. You eat some noodles, some pasta, you eat a piece of bread that's high in carbohydrates. You're familiar with the word carbohydrates. You know it's like bread and cereal type things. It gives you generally instant energy. The storage form of sugar in animals is known as glycogen. The storage form of sugar in plants, it is known as starch. Those are both examples of polysaccharides, okay? Now, how do we build up and break down organic molecules? All of them. All right, I want you to take your hands right now and go like this. Let me see. And repeat after me. Dehydration synthesis builds up, and put your fingers like that. Hydrolysis breaks down. Dehydration synthesis builds up by removing water from the solution, and hydrolysis breaks down by adding water to the chemical that's trying to be broken down. All right, so on the test you remember this: up, down, dehydration synthesis builds up, hydrolysis breaks down. Dehydration synthesis, if you take a look in figure 2.16, you are removing water from the built-up compound. All right. Let's take a look at figure 2.15. It actually shows an amino acid. We haven't talked about that yet, but and how water is removed from the system to dehydration synthesis, build it up, and then it shows water being added to the system and breaking it down. Those two terms you should be familiar with: how to build up and break down organic molecules. Lipids have a bad rap. Often you hear the word lipid as being a fat, wax, or an oil, and it's bad for you. Clogs your arteries, makes it chubby. Fats are known to have a lot of bonds. And if you look on page 60, figure 2.18, it's a great picture of a neutral fat. Each bond has energy, and each bond having energy means that when you eat it, there's more calories in it. So you can't see that, but anyway, that's figure 2.19. And fat underneath your skin is known as subcutaneous fat. And so you go like that, you can feel the fat. You have to have a certain amount of fat. We really have three types of fats. We have neutral fats, also known as triglycerides in your blood, and they're made of 3 fatty acids and 1 glycerol. We have phospholipids, which is a fat with a little phosphate head on top, as you can see from this picture. That's what we find in your cell membranes. We'll talk about that in the next lecture. And then you have steroids, which are little flat compounds, again, all on page. They're nice pictures on figure 2.18. These steroids are notorious for clogging up arteries. And I want to emphasize this right now. This is a picture of an artery, okay? When, you can think of an artery like a little tube like this, my cord, blood flowing through, going to your heart. And when cholesterol builds up on the walls of the arteries, we call it arteriosclerosis. And this is the problem. Listen, this is the problem with arteriosclerosis. Let me show you on the screen, as blood flows through the vessel, it becomes turbulent in the area that gets more narrow. And turbulent blood flow initiates clots. I repeat, turbulent blood flow initiates clots. So it's not that the clogged artery, totally gives you a heart attack. You can't have anything get through it. It's that it lends itself toward clotting in areas that are clogged up. So that's why I almost think, people over 55, 60 should have like a baby aspirin to keep the blood flowing. They almost made that a requirement, or recommendation rather, at some point, just to prevent cloggages. As you get older, everyone, you will develop little plaques on the walls of your arteries. Some have it more, some have it less, based on genetics, based on diet. But, even at your age, 18, 20, they've shown little fat deposits. That doesn't mean you should pop aspirin right now. I'm just telling you that the physiology of it is such that it fits with the anatomy, right? The cholesterol plaques on the walls of, let's say, your heart arteries or whatever arteries, can lead to increased risk of turbulent blood flow going through, swishing blood flow going through, which initiates clots. So again, let me reiterate. What do you have to know here? You got to know the 3 types of fats: neutral fats, phospholipids, steroids. Cholesterol is a type of steroid, and it develops on walls of arteries. Obviously, you've heard of the word steroids, like anabolic steroids, taking it to pump iron. That's a fat-based steroid hormone. Very true. But cholesterol is another class of it. Phospholipids you've heard about in high school being in the cell membrane of all our cells, so we need a certain amount. And last but not least, the general neutral fat, what you have in bacon, and that can be discussed a little bit in terms of saturated versus unsaturated fats. Some fats are good for you. If they happen to have a double bond in them, we say that they're monounsaturated, like olive oil, better for you. Coconut oil is terrible for you. It has a lot of what we call saturated fat. And a picture of saturated fat is shown in, I don't have the picture, sorry. You can Google it. Google coconut oil and look at the chemical structure. And man, you will see all single bonds, and they are notorious for building up fat on the arteries of people. So, interesting about coconut oil. People just don't know that. There's a lot of bad oil. I mean, obviously bacon, grease. So the more saturated the fat, you should always read labels. If you don't understand what the label means, don't eat it. Saturated fat has a lot of single bonds between carbon and hydrogen, and that's somehow bad for you. Monounsaturated has a double bond, and looks like an equal sign. And somehow, monounsaturated fats are kind of better for you. All right, they're good for you, like olive oil. So, an interesting point. Okay, continuing. Let's look at the amino acids. If you look at figure 2.19, I've got an image of amino acids, and figure 2.2, an image of the amino acids built up into long chains. The basic structure of an amino acid, and I know one question on the test, basic structure is that there's a central carbon for every amino acid. They all have a hydrogen. They all have what we call an amino group, an NH2, and they all have a carboxyl group, a COOH. All right? You have to know the amino group is kind of dangerous for you, and your body has to get it out through the kidneys. Carboxyl, not so much. It's recycled, and it's a COOH. And then there's a variable group. You have 20 different types of amino acids, each having a different variable group. And as we get the structural organization of the atom, we have, I guess we can kind of look at it like this. A single chain of amino acids is known as the primary structure. In figure 2.20, the primary structure is just a string of amino acids, as you can see on your overhead. Then if you take the amino acids and you turn them, like a slinky, ever seen a slinky? That's the secondary structure. Or if you turn it into a sheet, a blanket, then, where do I have a blanket? Anyway, like a covering, that's a beta-pleated sheet. That's secondary level of structure. If you take that blanket or that slinky and mush it around like a nasty little kid mushes a slinky, then you have a tertiary structure. And a quaternary structure is when two or more tertiary structures are bonded together, okay? And that makes a quaternary structure, such as hemoglobin in all of your red blood cells. So that's the structural organization of proteins. And it makes us have proteins that are either fibrous or globular. Fibrous proteins are strand-like. Feel your hair, that's a fibrous protein. It's water insoluble. It's not going to just dissolve. You don't take a shower and it disappears. So it's got structure, structural protein. Pull your face a little bit. That's collagen and elastic fibers. Feel your face. That's keratin protein. It's all structural. It holds you together. Fibrous proteins hold you together. Globular proteins are compact spherical proteins that are chemically active, right? They're functional. They're water soluble. They dissolve in your blood and they get things done. Enzymes, antibodies are examples of globular proteins. I think I have a true-false question on the test about fibrous versus globular proteins. So for example, what's collagen? It makes up your skin and holds your skin together. It's fibrous, right? What's an enzyme? Globular. So you should know the difference. Speaking of enzymes, since you asked about enzymes, here's an enzyme, a picture. An enzyme speeds up a chemical reaction. It acts as a catalyst to speed up a chemical reaction. And there's a little active site, in other words, a little site like has a little hand that binds to some chemical that it acts on. And that chemical is known as a substrate. So it binds to a substrate, and we say lowers the activation energy needed for the reaction to happen. In other words, it gets things done. I kind of think of them as, you ever been on a blind date? I was on a blind date once. Terrible. That's a long story, but you know, you don't have blind dates anymore because of Facebook, you know. But years ago, you didn't know what you were getting. So anyway, my point is, it's like a matchmaker, and an enzyme gets things to happen. It says, "Oh, why don't you two go out on a date? Here's $20." Anyway, and then that's a matchmaker. So an enzyme comes and makes things happen, either breaks things up or brings things together. So, you know, you ever have a friend that's terrible, breaks up your relationships? That's an enzyme too. So anytime it ends in an ASE, everyone, it's an enzyme for the most part. There's a few examples, renin, carboxy, what the heck is it? Trypsin, that doesn't end in ASE, but for the most part, enzymes end in ASE. So lactase breaks down lactose, all right? Maltase breaks down maltose. Lactase is an enzyme that breaks down milk sugar, lactose. If you're lactose intolerant, then you don't have lactase as an enzyme to break down lactose. I just want to tell you though, 70% of lactose intolerance cases are misdiagnosed. So you got to be careful about those diagnoses. I just want to say that, just like the gluten-free diagnoses. Often it's not the correct diagnosis with these digestive things. It takes a long time to figure out what you're allergic to, and it can even be psychological. So there's a lot of things involved. Very, very controversial aspect of nutrition. Nucleic acids, that's your genetics, DNA and RNA. We inherit it. Most people know and have heard of DNA and RNA. We inherit our DNA, and nucleotides are the building block of nucleic acids. And I just want to skip forward to figure 2.22. It shows you a nucleotide, which is made up of always a phosphate, a sugar, and a base. All of these bases are different, and as you know, that's the base, A, T, G, and C, adenine, guanine, cytosine, and thymine. Those are the code of life, right? Your bases are the code of life, and that's what gives us our unique sequence. Last but not least, you should know that nucleotide, the most famous nucleotide of all is ATP. ATP energy, and this is a picture of it. 3 phosphate groups joined together by high energy bonds, an adenine and a ribose sugar. All right, the phosphate and the sugar, the deoxyribose sugar and the phosphate forms the kind of rungs of the ladder, excuse me, the verticals of the ladder of the DNA, and the base forms the rungs. Now, I want to do a quick demonstration. Hold on, let me see if I have anyone available to discuss ATP and how energy is formed from one thing to another. Everyone get out a dollar bill and have a friend next to you if at all possible, okay? And I want to show you, let me just get a volunteer. I got to get one of the kids with a dollar bill. Anyone around? Where's your mom? All right, I'm going to get one of the kids to demonstrate a good barroom trick for you guys. And basically, the principle behind it is take a person, and those of you who've taken my class, anyone who's had A&P1, don't give this away in the chat room. You have to catch the dollar bill, and you can bet someone, bet someone the money that they're betting, that the dollar bill, or however much, $20 bill, if we have inflation, bet the person that they can't catch it. They got to keep their hand stationary like this. Make sure you see this. And then they got to catch it when the other person drops it. All right? Conrad, come. Hey, come on over, mister. Put your hand right here. Take a seat.
Okay.
Now, put it right here. I'll give you the $5, boy, if you can catch the dollar bill. You guys see that? Oh, you didn't get it, mister. You're a loser. Come here. We'll try double or nothing. Double or nothing. No, don't be greedy, mister. All right, hit the road. That's it. You owe me $10. Now, the kid's angry at me, of course. He's furious. I'm kidding. You don't have to pay it back. Anyway, well, he stormed off. Well, that's a way to get into a family feud during the coronavirus. So, you know, the answer is you can never really catch the dollar bill because there's too many nerve impulses from your brain to your hand. It's about 6 feet, right? 2 meters. So as a result, any person, and I did this in the old bar tricks in my college days, and believe me, you can get yourself beaten up. Because when someone's drinking, they're angry, and as well, they are not able to catch the dollar bill. 1 in 1,000 people can catch the dollar bill. So you could do it with your family member. It changes, right? It changes your stored potential energy into kinetic energy. That's why I like that demonstration. You move your finger, that's kinetic energy. You send electrical energy from your brain, all that stored, to your hand. That is electrical energy, sodium and potassium flowing. It's just that it can't get there fast enough. So the potential is changed into kinetic, and that kinetic energy is the mechanical energy of movement of the muscle. So I like the demo. It's fun. I always do it. Now I'm going to have someone furious with me after we get off. I got to do damage control. He does not like to be on stage. But anyway, all right. Why don't I unmute, do the chat room, and let's march on. That's it for the lecture. I want to unmute everybody, and I want to, just take any questions. It's quite a bit of material that we cover. This is the most material we're going to cover in one. It's not worth working him up because you know what? He will be nasty all day. That's the problem. So if you have any helpful hints on dealing with a 13-year-old, let me know because it's not easy. All right. So anyway, no, it's more fun in the classroom because I usually have you demonstrate it, and I will bet you, and then you get pissed because I take the money, and then at the end, president said I'm not allowed to take the money, so I have to give it back. But it is a little fun. It's a nice, actually, it's a fun trick that you can always give. Yeah, I shouldn't. It's a fun trick. What you could do to your parents, but you have to make sure they don't grab. Keep it on a stationary. Let me show you my hand. Keep it on a stationary spot. All right. Otherwise, someone will just grab it. So make their hand steady, and then you just drop it. And they won't catch it. It's really fun, and it can tick people off. All right, and I am known to aggravate. So anyway, what else? What other goodies? I have your screens up. If you want, you can chat, or you can ask any questions. I don't know how you feel about the lecture. It is quite a bit of material, but now we're done with it. We'll move on to chemistry, and we only have a total of 10 lectures altogether. So we're 1/5 done with the course. There you go. So. No, the test's going to have 3 chapters, everyone. We had, we're going to have chapter 2 and 3. 3 comes on Tuesday, and we'll go from there. So, test is Wednesday. I hope I didn't misspeak. What test is Wednesday? Tuesday's cell bio. And then Wednesday, I'm just going to email you the test. We're not going to meet. I'll just email you the test at 9, and then at 9:45, you got to email it back. And I think you'll be well geared for it. Read through the notes. I think you'll be able to answer everything through the notes, but you should read the text to, understand the notes, especially because we're not seeing each other face to face. So, what other goodies? Can you explain covalent bonds again? And feel free to ask questions, everyone. You're more than welcome to unmute too if you want to chat. But covalent bonds are, let me go over all 4 of the bonds, okay? All 4 of the bonds. And let me put this back up to that part. Covalent bond, you got to think of it as relationships, right? Have you ever been in a relationship where one person's a taker and one's a giver? Well, here's the answer. That's an ionic bond. You give up the electron. The person giving it up is the cation. The person taking it is the anion. They're both benefiting, right? One's giving it up, one's taken. However, I just want to say covalent is the opposite. Covalent's when you equally share. You do the laundry one day, I do the laundry the next. You cook a meal one day, I cook a meal the next. Covalent bond is equal sharing. Which one's more stable, Taylor? The covalent bond, right? When one's given and one's taken, one gets irritated after a while. You see that? That's what breaks up. That's why they break up in water. You got to think of it as relationships. Have a little fun with this. You know, if you've ever been in a giver and taker relationship, if you're just giving and giving, you're out of there. And that's happened to all of us. Covalent is the best, you know, where everyone's equally sharing. Is it just a lie? Maybe. And that's why we got polar covalent. Most of the time, relationships are unequal giving, unequal taking. I take a little more than I give, so I'm slightly negative, like an oxygen. My wife's probably slightly positive. She gives a little more. And the boy, well, he's just furious. He's like a hydrogen bond. I shouldn't mess with him. Bonding between hydrogen atoms are unstable, right? So two water molecules can fall apart. A review date. We don't really have a review, but we can, you know, make it a review after the lecture tomorrow. That can be fine too. You know, I have fun discussing this stuff. I don't have a great picture of ionic bonds because I have it in the notes, and covalent bonds, but the images in the text should be real nice for you. You know, let me give you some guidance with the textbook. You know, when I teach this book and I teach it in general bio, we teach it with societal applications, and I discuss, you know, things like, what are you eating that's not healthy for you? Bologna, salami, you know, pepperoni, whatever. And so we analyze foods. You might want to do that on your own, but it's beyond the scope of A&P because this is such a proscripted curriculum. You know, like I've got to give you all these 10 lectures. We don't have time to fool around with a lot of philosophizing about diet, but you should, in your own mind, think about, you know, as you read the chapter, all the different foods and chemicals we put on our body. Like the European Union bans over 1,000 chemicals that we allow in, you know, creams that we put on our body, and foods that we eat. You know, the U.S. allows a lot of different substances in food that other countries don't. You know, who's right, who's wrong? This is something that has to be thought about. Like BPA, bisphenol A, in the lining of cans has finally been banned, and I actually kind of pushed for it in one of my books. You know, they finally banned it because it's linked to reproductive cancers and diseases, etc. But, you know, it all costs money. As you don't put certain chemicals in, food spoils, you got to do other things. So there's a philosophical component of this lecture that I don't get into even during class. You know, I may chat a little bit about it, but, you know, something to think about, talk with your family about. Hopefully this course will make you think and reflect and talk over the dinner table with your parents and your family members and your friends, because it helps you to think about things. I don't want it to just be dry. It is kind of dry because I had to go through 1 hour of lecture of chemistry. But on the other hand, you know, go through it, you know, organize it, you know, first start with the organics, look at Rutherford's model, then go on to the different chemical reactions, then go on acids, bases, more hydrogens, more acidy, less hydrogen, less acidy, and then go on to the 4 organic, you know, molecules. And that's really what we did today in a nutshell. But, you know, next class we're going to do cell bio. We'll see each other Tuesday at 9 o'clock. And you can feel free to email me there. You know, if for some reason, and I don't know, sometimes, you know, if we can't make it, even myself, I intend to make every lecture. But if I can't, and I don't have internet access, I will upload it on YouTube, the lecture, and then I'll tell you to look at the lecture. A lot of faculty are just doing that, and I don't like it. I like to meet, you know, so we can answer questions. But it may happen. I'm not sure at some point over this summer. All right, and I'll always email you and tell you. But I intend to be here each lecture, and, you know, that's what we'll do, 9 o'clock. If you can't make it, then you also can go to that YouTube channel. I don't know if you've gone to it yet. If it works, it looks like it works to me. So, oh, do I think the campus will be open? You know, campus will be open, I think, but I don't think we'll ever close down again. I don't know if the science pushes for that, but I do think, from what I heard, liberal arts and science is supposed to be online. That's what I heard you tell me, and that's last I heard. But nursing is not online due to the clinicals and the nature of it. And other, you know, like carpentry, welding is not going to be online. I don't think they know. So it's such a good question. But I'm planning honestly either way. That's why I'm putting all the stuff. I'm recording all the lectures. That's liberal arts told us to record all the lectures with the intention of being online. So I don't know. So sorry about that I had to repeat the first part of the lecture. I keep forgetting it every time because, we chat and then I forget. Anyway, no, hopefully enjoyed aspects of today's lecture. And I don't want to hold you up further. You're welcome to go now, but you can stay behind if you have questions about the lab or anything else. And then, go on the chat room and say you're going to stay behind. Otherwise, I'm going to get off in a couple of minutes. So keep me posted. And other than that, finish reading chapter 2, move on to chapter 3, and that'll be it for the first exam. The parts of chapter 11, parts of all of 2, all of 3. That's exam 3, which will be 40 questions. So, all right, bye. I'll stay on in case anyone wants to stay the next 3 minutes and ask any lab questions or anything that's unclear. And then I'll go too. And I made $10 off the kid. Go out and make some money off your family members with that trick. What parts of chapter 11 will be on the test? Chapter 2, 3, and 11 will be on the exam. Yes. Textbook not giving you access. They got to give you access. Call up KendallHunt.com. You can call up Kendall Hunt. Go to KendallHunt.com. You can go right to their chat room. They're very efficient, and they will get you what you need with the code. As far as chapter 11, I have it in the syllabus. Whenever I load, did you buy a new code, Maxine? Or is it an old code? Because the old one expires. If you got a new code, it should give you the access right away. A new one, really? If there's any problem, CC me, and I'll talk to them. Let me answer the question on chapter 11. I'm just going to go through this very clearly. The intro to the human body. You got to know pages. I mean, really, the case of a saved star. I'm not going to test you on the story, okay? But page 382 goes all the way, this is what we did, to 395. You got to know that. And then the rest of that chapter has a lot of histology, which I do not get into yet. You're going to have that on exam too. Then you have to start with page 405, and it goes to page 414, and that's what you have to know out of 11. Yeah, let me know, Maxine, what goes on. Yes, thanks, Tanya. Let me know what goes on with that code. Go to KendallHunt.com. Did you buy it? May I ask? Did you buy it from the bookstore or from the website of the publisher? Oh, you bought it on Kendall Hunt? Well, then they definitely should be going. Go right to them, say it doesn't work, and they will walk you through. They're pretty good. They're pretty good, and I would get involved too if you want. What else? Other goodies. Was it clear today? I mean, did it make sense, the lecture, the chemistry? All right, that's good. That's good. Go through it, and it will be open book, guys. So, I mean, it's not like raw memory. You got to be familiar with it, and I think that'll help. Good. Any questions on lab? Anything else? Oh, good. You took notes, read the chapter. That's great. Good reading. Hopefully you don't fall asleep while you're reading. I read the encyclopedia to put myself to sleep. It takes me about 3 minutes. So, you know, hopefully you last longer than that with the chapter. Anyway, good. Well, good. You can also email me anything over the weekend and enjoy. All right, very good. I think we seem to be coming to an end of the meeting. All right. Keep me posted.